In this final video, we're going to look at the probability of a union, which is another very common event that we want to consider. The probability of a union is just that. It's going to be the probability of one event or the other event occurring. So it might look something like this. You might see the probability of A union B. So in other words, that's the likelihood that an element exists in one, the other, or both. We can write this in a nutshell as the probability of A and B plus the probability of A and not B plus the probability of A not and B. In other words, these are just the three circumstances that are all separate. You can't have A and B occurring and simultaneously having A and not B occurring. So we don't have to worry about any overlap between these two probabilities. But let's go ahead and take a look at an example. Let's say that we have a couple of bridges that maybe go across a little river. So here we have some little river, and I think I'm going to get a little artistic here. I'm going to try to make this look pretty good. So there's our little river, and let's suppose that we have two bridges that one can take. Maybe there's a bridge over here, and there's a bridge over here. And we're going to assume that these bridges could actually, I can't think of what they're called at the moment, but that these bridges could actually raise up to allow boats to come through. So these guys can elevate. Now, you're driving down the road, and maybe you get to choose, maybe there's some sort of fork here where you can choose to go along bridge 1 or bridge 2, and you want to know what's the likelihood that you show up at that juncture, or you show up at one of the bridges and one or the other is down and allows you to go through. Well, let's go ahead and suppose that the probability that bridge 1 is down and that therefore you could pass through is 0.6. In other words, 60% of the time when you get to bridge 1, it's going to be down, it's going to allow you to pass through. We'll also just assume probability of bridge 2 is maybe 0.5. I don't know, maybe there's some sort of dock in here, and so sometimes most boats come through this way and dock down here, and it's less likely that this bridge is open, maybe because a lot of the times when it's up, that's just because of some boat needing to get there. Okay, well, we're going to assume that these happen independently of another. Whether this is a good decision or not doesn't matter. For now, we're just going to assume that they're independent. And what do we want to know? Well, we want to know what's the probability that you get there and at least one of the bridges is down. At least one bridge is down. Well, the one way we could do that is we could say that's 1 minus the probability that they're both up, and that means if we take away the likelihood that both of them are up and therefore letting boats through, we take that away from 1, then that's going to give us the percentage of times that at least one of those two bridges is down. But I want to approach this in a slightly different way. I want to say that what we're looking for is the probability that bridge 1 is down or bridge 2 is down. So that's going to be the probability of this union. Now, one thing we might say is, well, that's just going to be the probability that one of them is down plus the probability that the other is down. And the problem with that is that if we kind of define our sample space here, and I'm going to be a little vague about the sample space, but I'm going to say that this is the set of all times that bridge 1 is down, and this is the percentage of all times that bridge 2 is down. Now notice that there's an overlap because there might be times where both of them are down, and therefore you could choose which one you want to take. Now, if the probability of bridge 1 being down is 0.6, so the probability that bridge 1 is down is 0.6, and the probability that bridge 2 is down is 0.5, it might be tempting to just add these two probabilities together. And the fault in that, of course, is going to be that if we add 0.6 and 0.5, then we get an overlap, right? We've basically double counted this area. And so some of these 60% of times, the bridge 2 is also down, and some of the 50% of the time, bridge 1 is also down. So if we add together 0.6 and 0.5, you'll notice that what happens is that, okay, we add that, look at the likelihood or the percentage of time that that event happens, and then if we also add this in, then you can see that we've counted that intersection twice. So to handle this, the fact that that got double counted, we're going to take the probability of bridge 1 and add it to the probability of bridge 2, but we're going to subtract away the percentage of times that bridge 1 and bridge 2 are both down. Now, since these are independent events, that's just going to be the product of the two probabilities. So 0.6 plus 0.5 minus 0.6 times 0.5. Again, we're just removing one of those shadings. So essentially, we're saying, hey, you know what? Let's go ahead and remove that overlap there one time. And therefore, now we're getting a holistic picture of the likelihood of one or the other happening. So this is going to be 1.1 minus 0.3, which is 0.8, which seems more reasonable. 80% of the time, at least one of those bridges will allow you to pass through. And that seems like a pretty good deal. Okay, well, the other way we said we could compute this is by adding the three separate pieces together. What we know about sets is A intersect B is the overlap here. A and B complement is, well, in this case, this portion here that's shaded in pink, and the probability of A complement and B is basically this shading over here. So these are three distinct probabilities that do not overlap. But one optimal way to do it is like this, where you could just add the two probabilities together and subtract the probability of their intersection to account for that overlap. One other way we could visualize this to make this more clear is to draw ourselves a little contingency table. And we'll just say this is corresponding to bridge 1 being down, bridge 1 not being down. So we know that bridge 1 is down 60% of the time, therefore it's up the other 40% of the time. And again, this is going to account for the 100% of all situations. Now we can do bridge 2 here, and bridge 2 being up right there. And we know that this is 50% of the time the bridge is down, and 50% of the time the bridge is up. Now, because we want the cell probabilities, well, the probability of B1 and B2, because of the independence of these two events, is going to be the product of them. So 0.3, which is 0.6 multiplied by 0.5. In this cell here, that's the probability that B1 is down, bridge 1 is down, and bridge 2 is up, which is 0.6 times 0.5. That's again going to be 0.3. The probability that bridge 1 is up and bridge 2 is down is the probability that bridge 1 is up, which is 0.4 multiplied by the probability that bridge 2 is down, which is 0.5. This gives me 0.2, and I'll also have a 0.2 here. Now, if what I did is added together the probability of B1, which is basically this 0.6, and that 0.6 comes from, we add those two together, and we add that to the probability of B2, which is 0.5, which is the sum of these two values, we can see that this 0.3 gets counted in twice, and that's exactly what we're subtracting away to account for that overlap. This is just another visual way to see that. If instead what I wanted to do is to just add up the three probabilities that I know don't overlap, namely the probability of B1 and B2 both being down, plus the probability of B1 being down and B2 being up, plus the probability of B1 being up and B2 being down. Well, now I can grab these probabilities. I see that this is equal to 0.3, this is equal to 0.3, and this is equal to 0.2. And if I add those three together, you notice that what we get is 0.8. That's just a second way to do it. One final way, the third way, is we said that the probability of having at least one of those bridges up is 1 minus the probability that they're, the probability of having at least one of the bridges down is the probability of 1 minus the probability of both of those bridges being up. Well, that's going to be the 0.2 here. 20% of the time, both bridges are up. And if we subtract away from the 100%, the only event that we don't want, we get 80%, which is the same answer we got here, and it's the same answer we got by using the probability of a union. So to make this more general, we could say that the probability of one event or the other occurring is equal to the probability of the one event plus the probability of the second event minus the probability of both. And all we're doing here is just removing that portion of the Venn diagram or the portion of the contingency table that got added in twice.